Today we will cover 4 topics. And the first 2 topics, I already give you some introduction on the first 2 topics. And the last 2 topics will be new stuff for you. And this PDPSD stands for positive definite and positive semi-definite matrix, negative semi-definite. The definition for defined linear functions. For a solution to be exist, we have mentioned that from previous time, that given an ODE, how we can evaluate the existence of a solution, right? So given this nonlinear ODE, okay, with some initial conditions, we can evaluate this behavior, these solutions, based on the fx. So if fx is continuous in some local area, local region R, right? Then if it's continuous in this region, then given which contains the initial conditions, there will exist a solution for this dynamics with initial condition at S0. So an example of this, which have no solutions, if you start at 0, okay? Because this fx, which is the square root of x, is not defined at 0. This is initial condition at 0, okay? It's not defined, so which implies this fx is not continuous. For uniqueness, there's one more condition, which is the partial of capital F have to also be continuous, right? Which implies fx is Lipschitz in the same area R. Then if you have any initial conditions x0 in R, then it guarantees you have a solution in this local area R, okay? And this is another example, which says if you start at 0, you have multiple solutions, which is solution 1 and 2, okay? Both are the solution to these ODEs because fx is not Lipschitz, especially at 0. You might heard this before, sliding mode control. It's fine that you don't know what is sliding mode control, but if you heard about this, it's great. So there's a problem in this sliding mode control, but no one in real applications talked about it. But it's really caused some problems in mathematically. So the problem is in this system. So here's U, right? This is U, the control, external control. But for this first part, it's open loop dynamics. So this part is the control. Here is no control. It's natural dynamics. So if you don't control, it could be unstable. Okay. For example, like fx is x, right? And this solution, which is a linear system, right? Okay. We assume that fx is x. This system will be unstable, right? The solution you can solve for this because it's a linear ODE, and the solution is unstable. It doesn't converge to 0 in time. You can add the controller. Here, xt will go to infinity as t go to infinity, right? X increase with time. In this case, after you add another external controllers, your solution might change. Might converge to 0 as t go to infinity, right? So this is from the contribution of this control. But this control so that's called closed loop dynamics, right? Okay, it's kind of feedback after you add this term. If you are interested or you can evaluate the solution of this ODE, okay? Let's say, did anyone know what this function looks like? So sine function. When x equal to 0 is 0. X, when n is -1, if x is smaller than 0. So the question is this function, sine function, continuous? Is it continuous? No, right? There's a jump at 0, so it's not continuous. So, which implies even it's continuous, this is not continuous. The summation is not continuous, right? So, it's not continuous. Not continuous. Or C0, right? Not continuous. As we taught from previous week, here it says if f is continuous in the region, in this R region, where the initial condition located, right? Then you have a solution. But now here, it's not continuous at 0, right? If your initial conditions is our objective, but if you start your initial condition is at 0, where this is not continuous, then x, the solution doesn't exist. Okay, but in reality, in real applications, sine function, because of the dynamics of the mechanical systems, this doesn't exist. You cannot really do a high frequency switching, right? When you are on the neighbor of 0, if you are on the right hand side, a little bit right of this 0, otherwise it's -1. But it's hard to really switch that fast for your mechanical systems. So in real mechanical systems, usually it's continuous. But for mathematical model, it's not continuous. In the real case, if that's true, which is not continuous at here, and if you start from here, I don't know what's going to happen, but the solution doesn't exist. So if you apply this kind of control to your motor control, the motor doesn't go anywhere. It just oscillates around 0. But actually you have a power input, right? You have voltage, you have current. So the system absorbs the energy, but it doesn't generate any output work. So the net energy will be converted to heat and dissipate to the nature. And eventually the temperature of motor will increase until it's burned out. Okay. So this is not a good controller in reality. Okay. So now we have bridged the gap between existence, uniqueness, and to this example, right? To this real dynamic system example. So is that clear? So next, reachable set. So reachable set is the same as controllable set. If you can read that definition, basically it means the controllable set. Set means a collection of states, x. So given a nonlinear system, which is a function not only x but also u. So basically it's a closed loop system because you have control. So let u be an open set of dimension m. X0 bar is Rn, the reachable set defined as Ru, which is depend on the initial condition and capital T for a given non-zero time. It's defined as a set of all x, capital T, where this x from 0 to t is belong to the Rn set, and the control is belong to Rm set. So this set is defined as a reachable set for this dynamics. So basically this is reachable set u. So assume initially you are here. Okay, you are here, which is x0, right? Initial condition here. Initial condition, you start from x0 bar and you apply some ut belong to this set t. Okay. So this point represent in this set. Okay. And next time, after you at this state, you apply a control, you might reach to the next point, which is xu, right? And you apply another u. So if you repeat this, you might have this kind of configuration. So each point represent a reachable set. Okay, so the collection of all these points is a reachable set, which means if the system is controllable, this point should cover the space. Given any state, you can use a control to go anywhere in this set, which is reachable. So it's called reachable set. Let me give you an example. A car. You can apply, given a car and state x. Okay, it could be x1, x2, could be position or velocities. And here is your acceleration, which is similar to the amount of gas that you put into your agent, or the angle of the pedal, right? The point here is given a state, the amount of control you put into the system. This combination is a point in this set, okay? So you can imagine that the next state after x and u, after giving us current state and you put some control input, the system will reach to the next state, right? X, t, right? And at xt, you put another u, which is maybe a, t, okay, and so on, right? A reachable set will be a point here, a point here, a point here. Every possible state, the collection of all these states are reachable set. So let me ask you a question. Car cannot fly, right? If you call some set here, which is z equal not equal to 0, or the height is not equal to 0, this set is not reachable for this dynamics, controllable of the linear systems. So we have mentioned controllability for linear system and nonlinear systems, right? For any nonlinear systems, you can linearize the system at any point. So theta is equal to the x1 state, okay? And theta 2, so x1, x equal to x1 and x2, which is c times theta dot. This is theta, okay? And you have in here the pendulum, the length of pendulum will be L. And you have mg here and some t here. Okay. So the dynamics of this system is represented at this ODE. So it's nonlinear, right? Because your state, which is x1, is a sine function. But this nonlinear system can be converted to a linear system, 线性化. You linearize this. So the problem is for nonlinear system, which is x1 dot x2 dot I is the inertia. U control input. Okay. We want to convert to a linear system. Okay. We want to convert from a nonlinear system to a linear system. Okay. Which means that you need to find a way to decouple these nonlinear functions. And the way is using this approach. The relation between the A, we say in general, x, u. Okay. This. How you convert a nonlinear system to a linear system. So the relation between this f and a is a equal to partial x, partial f, b equal to partial u, partial f. So it's clear that the dynamics is this, right? You can represent by this. But what does this mean in this picture? One more important thing is you have to evaluate this because it's a function, right? 你做完 partial 它是个 function 的 It's a function of x and u because f is a function of x and u. So after you take the partial, you need to evaluate where is the point of interest, right? So if you are interested at x equal to x0, u equal to u0, then the MS will be different, right? It's a function of x and u. So given different point of interest, this MS will be different. That means when you linearize a system, you need to choose at which state, given which control input. Okay. And the selection of these two have a constraint, which is x0 and u0 has to be 0. Okay, which means you have to evaluate at the equivalent point. So if you are interested at this configuration, say 30 degree, I want to see at 30 degree what's the linear dynamics of this pendulum. And you can imagine that the dynamics is totally different compared to at 0 degree, right? The partial of x, f, with respect to x is this function, okay? In this matrix, it's a function of x, as I mentioned, right? So you need to substitute what is the point of interest. So next, we substitute x0 and u0 to this. Then you got a constant matrix. So now A becomes a constant. B is become a constant, which is the spirit of the linear system. Remember, in the linear system, this had to be a constant. So this is the linear system at this state, right? So if you change x0, maybe 30 degrees, so you put here as pi over 6, which means your MS will be different. So the linear dynamics is different at here and different at here. So you can imagine what's the difference, why you need the nonlinear controller. If you use a linear controller, you can only apply to this kind of system, which only guarantees stability around this point, right? Because when you are away from this point, the dynamics totally changed. And the same controller cannot guarantee stability for this system, right? So if you design a nonlinear system, it guarantees that no matter what is x1 and y1, no matter at which state, this controllability, this u guarantee the stability. So this property is said local controllability. If you linearize any nonlinear system, the stability is only controllable, or the stability is only local. Okay, everything is local. The properties are local. Controllability is local. Stability is local. Here is the math, the background over here. Okay, so here I told you how to linearize the system. So given any nonlinear system, the linearization of this nonlinear system around some point can be approximated as this. And the delta x is defined as perturbation around the equilibrium point, or around x0. U is the perturbation around the U0. Okay, x0 and U0 is here. And your A will be evaluated is the partial of f evaluated by x0, U0, same as U. Okay, and these are the elements you construct the linear system. So here, this delta you can consider it as you translate your x coordinate to by some x0 value. You transform your control to some U0 value. So you which is you move all your system to equilibrium point. At 0, U is 0. The 30 degree, which is pi over 6, the element in this A matrix is different. Okay, which represent the dynamics are different. So what is U0? U0 and x0 have to satisfy this, right? Because at that point, x0 will be stationary, right? If this is satisfied, it means at that point, this is stationary, okay? So another new concept is observability. So before we talk about controllability, here's observability. So what's the difference? The condition for a linear system to be observable is this matrix have to be full rank, okay? And this matrix consists of C, which is a row vector, and A, which is n by n matrix, okay? So before, we haven't mentioned about the second part, y is equal to Cx, right? Okay, here is fine, but what is y? Y is measurement. And C is just some coefficient, okay, some row vectors. So if your x, which implies your x is 2 dimension, right? Okay. Then your y will be, so what this says is y is the measurement, okay? And assume that in the example, the same previous example, right, car x, you apply some u here. X is x1, y x2, okay? Or position and velocity. And y is the measurement, right? And it's not full state measurement. It can only measure the first element x1 because of the C matrix. Okay, this says that in this system, only position is measurement. Okay, it is measurable. Okay, only this is measurable. This is not measurable. In this case, it's like a car. On top of the car, there's a LiDAR system. Okay, there's a LiDAR system that detects maybe here. Okay, there's a building, and it can measure the distance. Okay. So the building is like a remark. So implement this kind of rangefinder sensors. You only detect the range, okay, to these buildings. So using some estimator, this information can be used to estimate the location of the car, right? But the velocity of the car might not be measurable. Right? Of course, you can use numerical methods to evaluate the velocity, right? Given, for example, x1 t plus delta t minus xt, numerical method to get the approximate value of its velocity, but it's not reliable. It's very sensitive to noise. If you have some high frequency noise, when you take the derivative or numerical derivative, this guy will be totally destroyed. OK， 你微分它是对高频的东西非常敏感的。微分就是有点类似于在那个 Laplace system 你给它一个 s 嘛 ，s 你不就是一般什么 in Laplace system in s is equal to you put s equal to j omega right， 所以 omega 带进去，这个 omega 不就是 frequency 吗？当你有高频的 frequency 在里面的话，当你有高频的东西在你的 frequency 的话，你把它带进去，这个东西会变很大 ，OK， 所以这个东西会对高频的东西会非常敏感。So anyway, it's very sensitive to noise, okay, using this numerical method. So we don't recommend that you use approach to estimate x2 given x1, okay. So in this system, the manageable term is x1, not x2. So that's why you put 1, 0 here. Okay. So observability means given this measurement, okay, I know this is measurable. Can this one also be measurable? If both every state in here can be measured, can be estimated by this measurement, then it's observable. Controllability is evaluated from the input here, U, right? We given the input, we want to see if every element in the state is controllable. Observability is given this measurement the other way, the reverse way, right? Given Y, if every X is measurable. So the design of controller is a little bit similar to the observer. Okay, that's observability. So in the C matrix, you replace B. In the controllability, we evaluate B, A, B, right? Here is C, C, A. You just replace B by C. Because A remains the same, right? A is here and here. Because A is the propagation of states between different times. Okay, A is the natural dynamics. But C depends on which element, the input is from which element. Okay, same as B here. Okay. So here's controllability, and we have mentioned this before. Stability means it's always bounded. Unstable means it's not stable. It's not bounded. Okay, so here is these two are complementary. For asymptotically stable means it's same as stable, but it have to ensure as t go to infinity, the state have to converge to equilibrium point. Usually is 0, 0. Okay. This doesn't require the x goes to the equilibrium point. Okay. It just had to be bounded by some distance, epsilon. So next time, I will give you the positive definite function is looking like this. For example, x squared, x1 squared, or x2 squared. And semi-definite, positive semi-definite is something like this. And negative definite, and the above functions.